So continuing with polynomial interpolation, we've just seen a few different ways of obtaining one and only interpolating polynomial that you have for given data. And the goal for today is to get an idea of how accurate the polynomial is at its one job of interpolation, because when you are fitting given data, the idea is to find a function that captures not just data points you have, but is useful for evaluation at other points. Because often, if you have given data like a scatter plot of x and y values, in many, probably most applications, those points represent some underlying function that describes the relationship between x and y. So, so we figure that way, that we're not just fitting given x, y values. Really what we're trying to do is approximate some function f of x defined on some domain that's a continuum. So you have the values of f of x at select x values, and you come up with your polynomial Pn of x that matches f of x at these given points. So your interpolating polynomial satisfies these conditions, that at each x, polynomial is equal to the corresponding y, that's f of xi. But then what we want to be able to do is evaluate our interpolating polynomial at points in between these x values. So, and for a given function f of x, how accurately does this polynomial approximate f of x? So one thing to keep in mind is, so for convenience, I'm going to assume that all the x values are sorted in increasing order, which in examples they generally would be anyway. So if I choose an x that's in between these points, that's really what interpolation is. I mean, insert meaning between. But if I choose an x that is outside of an interval containing these points, like if I choose x to be less than x naught or greater than x naught, that's not interpolation, that's extrapolation, Leslie. Generally a bad idea, because you're fitting given data, and who knows how the polynomial over function is going to behave at points outside of the interval containing that data. But we're mainly interested in, we just want to call it interpolation. We want to see how our polynomial behaves at x's between the given ones. Okay. And this is something that we'll be able to quantify. So, there is a theorem that indicates how closely Pn of x approximates f of x at a given x. But before I state that, I'm going to recall a theorem that you're familiar with. That's a Taylor's theorem. So Taylor's theorem is repeated here. A function f of x that has sufficiently many derivatives is equal to this right here, which is the Taylor polynomial of degree n with center at x naught. And then, so that's an approximation of f of x that's accurate mainly near x naught. So f of x is equal to that polynomial plus this remainder. And here's the Taylor remainder. And notice that it looks very much like the next term in the Taylor expansion, except that this higher order derivative is evaluated at an unknown point, c, or as I like to call it, squiggly, instead of at x naught. And the reason why I'm mentioning Taylor's theorem is that the formula for the error in the interpolated polynomial has a very similar appearance to this. So here's the result, and this is in the textbook as theorem 7.4.1. That so f of x minus your approximation, which is Pn of x, is equal to this. And notice the expression starts out exactly the same as the Taylor remainder. You have so the error in a polynomial of degree n is the n plus first derivative of f evaluated at an unknown point. Admittedly, I'm being a little non-rigorous here. I haven't stated in these notes where the point xc might be located, so I should include that here. Okay. Where c lies in an interval containing the interpolation points and x itself. So the error in the interpolated polynomial at first looks like just like the Taylor remainder. The only difference is here we again have a product of n plus 1 linear factors, both here and here. It's just that in the case of Taylor's theorem, all those linear factors have the same center, which is x naught, the center of your Taylor expansion. Whereas in this case, the centers are your n plus 1 interpolation point. So you have x minus x naught, x minus x1, x minus x2, and so on. Okay. Now, what this means is, if I substitute xi in for x throughout this equation, then one of these linear factors is going to be 0, and the whole right side is 0. But that's what you would expect, because Pn of xi equals f of xi. So just because of these conditions right here, we would expect the left side of the equation to be 0, and sure enough, the right side is equal to 0 also. So the error in the interpolated polynomial is always 0 at the interpolation points, because Pn of x is designed to agree with f at those points. But unfortunately, that doesn't mean that this error can't get large in between those points. And I'm actually going to show you that today. Okay, so this is our polynomial interpolation error formula that bears a close resemblance to Taylor remainder, and there's going to be an exploration in the next section, 7.5, that will actually explain why this resemblance is no coincidence. Okay, so where does this error formula come from? So I'm going to give you an idea as a group. I won't present the whole group here. So this result is that so we're actually going to use this theorem is most easily proved using the Newton form instead of like Lagrange or power form. So there's a result. The theorem is also from section 7.3 that this divided difference accounting for x naught, x1 to xn, is equal to the nth derivative at an unknown point over n factorial. So this is true of divided differences in general. That when you have an nth order divided difference, and therefore there will be n plus 1 x values listed here, that is equal to the nth derivative of f over n factorial at an unknown point xc that lies in an interval containing all of these points. The way that this would be proved is using a theorem from Calculus 1, Rolle's theorem, repeatedly. I don't remember what Rolle's theorem even is. Okay. All right, I'm going to refresh your memory. Rolle's theorem states that if function f is continuous on interval AB and differentiable on the open interval AB, and f of A equals f of B, then f prime of C equals 0 for some unknown point C in the interval AB. Now, an important consequence of this theorem is it can be used to prove another theorem that you would have seen in Calculus 1, the mean value theorem. But I didn't bother asking anyone what that is.
That's okay. So if you have an interval A and B, then if you know that C is between A and B, you know that f of C is between f of A and F. No.
You're figuring the intermediate value theorem.
Yes.
Okay. You're starting out so well. Okay. Mean value theorem says that f b minus a over similar same assumptions on f, except they're not f a and f b are not equal, is equal to f prime of c, where c is some unknown point in AB.
It was whenever it was mentioned on one of the other notes. It was at the very end, and you said, "Well, why did I put that in there?" Maybe in before.
Wait.
Not in this one.
Oh.
No, one of the past notes. Your past notes, because it was mentioned.
In this class? I mentioned Rolle's theorem?
No,
mean value. Okay. Well, mean value theorem is so. One of my professors at Purdue, I had him for a class on numerical methods for ODEs. He considered Taylor's theorem to be the fundamental theorem of numerical analysis. I know I've mentioned that before. I'm not so sure, because I can't help but wonder if actually the mean value theorem is more important. Okay, so mean value theorem. Because if you define function g of x is equal to f of x, I'm doing this from memory, so I apologize for how stumbling here a bit. Okay. I think it's something like I need to check this. If I plug in x equal to a, I'll get 0. If I plug in x equal to b, that cancels. Also gets 0. Yes. Wow. I got it right first try. So that g of a equals g of b equals 0. So then you apply Rolle's theorem to G. So G prime has to be 0 at some point. And then you say, well, this derivative of this has to be equal to 0 at some point. And you get this. So that's your sketch of proof of V diagram. But I totally want to be doing calculus 1 today. But again, I have a hunch that, I mean, obviously calculus 1 here, I'm sure V diagram is covered. It may not necessarily be proved. Like I do it, but I haven't taught Cal 1 since 2011. One of my students in that class went on to become the runner-up in Miss America in 2015. Fun fact for you.
Don't pick up your class.
Oh, yes.
That was really special stuff.
Okay, so anyway, Rolle's theorem is used in a number of proofs of numerical analysis to prove formulas like this that involve a higher order derivative of f. Because the Rolle's theorem only makes a statement about a first derivative being 0, but then what you can do is apply it repeatedly to get this result, and also prove this error formula. Okay, but quite a long time to do that now. Okay, but if nothing else, you have a how long refresher. Probably because you have to take that major field test someday. Oh, I do have a proof here. Okay. I haven't looked at those in 2 years. So. Okay. So, all right. This is the topic that came up on the midterm about the Newton form. What do we like about the Newton form compared to the other forms?
Can be updated.
Yes.
Easily.
And that's exactly what happens here. So, so here's Pn of x in Newton form. So, and that interpolates at x naught up to xn. So then I define Pn plus 1 of x interpolates at all the same points, and I'm going to throw in a new point z. Okay. So then my new interpolated polynomial is equal to my old one plus this divided difference that has z thrown in, and then I have these linear factors. So this is just what the Newton form would give you if you write it down the divided difference table and all that. Now, Pn plus 1 of z equals f of z. So, if I look at what I want to get an expression for my error, f of z minus Pn of z, well, f of z agrees with Pn plus 1 of z, so I can replace f of z with Pn plus 1 of z. So now the difference between my function f and my polynomial is also the difference between two consecutive interpolated polynomials. But what is that? That's equal to the divided difference times all these linear factors. And this is a divided difference of order n plus 1 because there are n plus 2 x values sitting in here. And by this result up here, that's equal to a higher order derivative of f at an unknown point times all these linear factors, and that's the error formula. Okay, so this is not a full proof of the error formula because I have not shown you where this comes from. And I've been feeling a little guilt about that. But I also don't trust myself to show you a proof on the fly. I'll mess it up, and then I feel even more guilty. And yes, in my head wondering. Okay. Who knows, maybe it's buried somewhere else in the house. Okay, but are there any questions about at least this partial proof? And how the Newton form is used? They can mention certain things in the text here. So, okay. So this is a theorem that states that divided difference is equal, an n4 divided difference is equal to an n4 derivative of f over n factorial. And this is an expiration which you should be grateful that I did not assign. To prove this in the case of n equals 1 and n equals 2, that's not so bad. But then to prove it in general that involves Rolle's theorem. And so really you would be proving this. Ah, okay. I thought that's how it was done. Yeah, I'm just what?
Do you have to use induction?
Yeah, that could get pretty ugly. But, okay. Copy the equation here. And again, it relies on a Newton form. So I have P n of x in Newton form is equal to sum of divided differences. Okay. And we have a product 0 to of x minus x. Okay, so here we have divided difference times the product of linear factors, but when j is equal to 0, this is just f of x 0. And then here I have a product of I going from 0 to minus 1. That is called an empty product, which is defined by convention to be equal to 1. Just like an empty sum is defined to be 0. Now, this includes all the terms of a Newton form, but notice I stopped at n minus 1 because I left out the last term. I'm going to put that right here. I wanted it to be written separately. X in Newton form. Okay. Then what I'm going to do is I'm going to take an nth derivative of this. Nth derivative x. Now, this right here is a polynomial of degree n minus 1. What happens if I take the nth derivative of a polynomial of degree n minus 1?
The degree of that polynomial will be n minus 2?
Well, that's what we take for a derivative one time.
Oh, n times, yes.
Yeah.
Oh.
So it's okay, so it reduces the degree each time I take a derivative. So if I have a starting degree n minus 1, but I take a derivative n times, what's gonna happen?
Oh.
Try an example if you want your head. But
You will get a constant?
close.
0?
Yeah, because take x cubed, okay?
Yeah.
3x squared, 6x, 6, you take it 3 times, you go 1 beyond, you get 0. So derivative, that's why I wrote this separately. Derivative, this whole part's gonna be 0. Now, on the other hand, this is of degree, oh wait, it should be not n, but n minus 1. This whole polynomial is of degree n. Okay. This is of degree n. So if I just take the derivative of that n times, then you get a constant. The thing is, what is a constant? Now, this polynomial is equal to, if you multiply it out, you get x to the n plus a whole bunch of other things. And all those other things are lower degree, so you differentiate those n times, they'll all be 0. The only thing that's going to survive is the x to the n. So what happens? You differentiate once, and an n comes down. You differentiate again, and n minus 1 comes down, and so forth. So if I take x to the n and take the nth derivative, then there's a formula for what that constant is going to be. And so imagine, like, yeah, you're taking a simple example like x cubed or x to the 4th. You differentiate, 3 times or 4 times, and there's a constant. What's the constant?
Is it n?
It is n factorial. Yeah, so like in the case of 20 to the 4th, you get 4x cubed, 12x squared, 24x 24. Okay, so then what we're left with is, n factorial, and then I still have a divided difference that's sitting here. All right. So, so you kind of see how we get to this result. We have the divided difference we want. We have the n factorial we want, but here we have the n derivative of Pn. There's nothing in here about the derivative of f, so now we have to account for that. So now if we consider this function, f of x, I'll define e of x is equal to f of x minus Pn of x. Now see the interpolation error. So we have e of x is equal to 0 at all the interpolation points. x0, x1, xn. Now, this is where Rolle's theorem is used. Rolle's theorem says that if a function is equal to the same value at 2 points, its derivative is 0 in between. Well, here we have a function equal to 0 at n plus 1 points. So if I apply Rolle's theorem, the first derivative is f prime minus p n prime equals 0 at n points that are between the interpolation points. Okay. And all the interpolation points are distinct, so we have these n distinct points that lie in between them. Now I apply Rolle's theorem a second time. Now I have E double prime. That will be equal to 0 at n minus 1 points that lie between the roots of E prime. And it keeps going. So if I apply this repeatedly, I guess if I want to be completely rigorous about this, maybe it is induction, but these are the ways. So if we consider the order of derivative and the number of zeros, when there's no differentiation, there's n plus 1 zeros. If there's one derivative, we have n zeros. If there's two derivatives, there's n minus 1 zeros. The point is, the order of derivative plus the number of zeros always equals n plus 1. So now we have the n derivative. N of x which is equal to the nth derivative of f minus the nth derivative of my interpolated polynomial, which is the divided difference times n factorial is equal to 0 at one point. And I'm going to call that mysterious point squiggly or C. So now I have this equal to 0. So all I have to do now is rearrange this equation. So and solving for the divided difference, yields a final result, which is this right here. Okay. I've written two proofs like this on the fly, but this time worked out okay. Any questions about that? Not wondering how many of you are even tuned in. So now between that and what was done earlier, you have a whole picture of where the error formula comes from. Also, this is what I like about this subject, because in numerical analysis, you can have problems that involve only coding, or problems that involve entirely theory, or anything in between. Okay. Now, so now that we have this error formula, we want to use it to get an idea of how large the error could possibly be. Now, the error formula involves the n plus first derivative of your function evaluated at an unknown point. So, so what you need to do is figure out, well, how large can that derivative possibly be? For some functions, that's not a big deal. Like, for instance, if it's like a sine or cosine, so then you know it can't be bigger than 1. Or if it's a function that's always increasing, like e to the x, you can use that to get upper bounds. But other times it could be a pain. But that's a key ingredient of like how large can this derivative be. Then we have this other part of the error formula, the product of all these linear factors. How large can that be? In some cases, that can be determined analytically. It's really both cases. You're going back to Cal 1. There's a lot of Cal 1 in this class. But things we all forget. How to find a max or min of a function on an interval plays a role in both of these steps. Okay. And I have an example of this in the text. 7.2. I got too much stuff in this book. Okay, because I hear a function is sine x, and we're considering the first degree polynomial p1. Interpolates that x equals 0, x equals 1. So the error formula from the theorem would give us this, that it would involve the second derivative of sine, which is minus sine, evaluated at squiggly, over n plus 1 factorial, so 2 factorial, times x minus 0, because 0 is an interpolation point, times x minus 1, the other interpolation point. So we want to get an idea, is like, how large can this be? Now, as I mentioned with sine, that's, you can use the fact that sine is always less than or equal to 1, although here we can do a little bit better, because we're interested in squiggly between 0 and 1. But maximum of sine on that interval isn't 1, it's sine of 1, which is less than 1. So you can get a little, what's called a sharper bound than just than what you would get by saying, oh, this is just less than or equal to 1. Then, to see how large the other piece can get, we're looking at the maximum of this function on the interval 0 to 1. So what you do is you take the derivative, set it equal to 0, and you find it's equal to 0 at this one critical point, x equals 1/2. And then what we taught you to do in Cal 1 was also check the endpoints, max and min, but at the endpoints it's equal to 0. So that simplifies things. So you just plug a critical point into here, and you find that an absolute value is less than or equal to 1/4. So altogether, the interpolation error is less than or equal to sine of 1 over 8. So that's the largest the error could possibly be. Although if you were to actually apply the technique of finding the maximum to this function, what you find is the largest the error could be is really somewhat smaller, 0.06. Because this is only an upper bound on the error, and it can be a very conservative one. So in fact, in general, if you approximate a function by a secant line, so you take 2 points in the graph and form a line between them, then the I think there's a general formula for the error bound. It's like the maximum of the second derivative over 8 times the width of the interval squared. And that comes from this interpolation error formula. Okay, so any questions about this example where the error formula is used to get an upper bound? These are the things that I have to leave out of the midterm because I hadn't covered this yet. Yes, so your fellow students in 2021 have to do that. I might have to do the final. Okay. So in fact, I'll mention this in the notes. I was just saying. What's going on here? Oh, in the case of n equals 1, we show that the error in a secant line approximation of f of x on interval AB satisfies the following. Similar to what's in the example. X minus 1 of x is less than or equal to maximum x in over AB of f double prime, or an absolute value, over 8 times b minus a squared. Now, unfortunately, the interpolation error as given by this error formula can get quite large. And there's a famous example of this called Runge's example, where the function involved is a fx equal to this that produces a kind of sort of a bell curve-like graph. Like an integral minus 5 to 5, and we choose the interpolation points is equal to the integers. And I do have in here to tell you that. Okay. I'm just taking MATLAB stuff for later. I hope I don't run out of time, but that's why we're doing that. Okay. Now, if you look at the interpolation error formula right here. So two pieces of this, we have n plus first derivative, and then you have approximate linear factors. This part you can't really do too much about. I mean, that's just property of a function you're trying to approximate. But this is something we do have some control over. And that's the idea behind this next topic of Chebyshev interpolation points. So I'll show you in MATLAB how equally spaced points can end up not working out so well. So alternative is to choose your x value equal to what are called Chebyshev points, which are the roots of what's called a Chebyshev polynomial. So here's the definition of a Chebyshev polynomial that looks absolutely nothing like a polynomial at all. Looks rather tricky for a polynomial. But I want to point out, this definition applies only for x between -1 and 1. There is an extension of this function to x beyond this interval that actually uses hyperbolic cosine, which is even less polynomial. But I can explain why this, at least on the interval -1 and 1, this really is a polynomial. So first, go ahead and plug in some values of k, which agree. K equals 0, you get cosine of 0, which is 1. If I said k equal to 1, then I have cosine of inverse cosine of x. The cosine and the inverse cosine cancel, and you get x. So right there, the first two Chebyshev polynomials are just 1 and x, just like the monomials. Now, to explain why the rest of them are also polynomials, we can actually use a trig identity. Here we have these trig identities with cosine of the sum or difference, which is really weird because I was just teaching about that in my trig class yesterday. And they'll never appreciate their use here. Okay. So we have these. So now, okay. That's right. I can't show you how I get this from this because that's a homework problem. Okay. I was totally going to do it too because it's fun, but I don't want to spoil the fun for you all. Okay. So from these you can get this, what's called a 3-term recurrence relation. Each Chebyshev polynomial depends on the previous two. So here's some examples. Like a second degree polynomial is 2x squared minus 1. Third degree polynomial is 4x cubed minus 3x, and so on. There's one thing I want to point out though. If you look at the leading coefficients of all these Chebyshev polynomials, 1, 1 again, 2, 4. Considering that you have this 2 in there, that the Chebyshev polynomials have a leading coefficient of 2 to the n minus 1. I think proving that is another homework problem. My induction. Okay. Now, the Chebyshev points are defined to be the roots of tk of x. And I believe deriving this formula is another homework problem. Okay. Instead of being equally spaced, they're actually cosines of equally spaced angles. And that has the effect of clustering them near the boundaries of the interval minus 1 to 1. Now, how is this useful for making the error smaller? Here's how. Using the statements I just made, that the leading coefficient of tk of x is 2 to the k minus 1. And then with the xj being the roots of a Chebyshev polynomial, this right here is a factorization of the Chebyshev polynomial tk of x. But tk of x is also defined to be a cosine of something, which means tk is also less than or equal to 1 on this interval. So now what that means is if I return to my interpolation error formula, and if I choose x naught, x1 to xn to be the roots of tn plus 1 of x, then I get the following. That I still have this, that doesn't change. But since this has to be less than or equal to 1, this whole product of linear factors has to be bounded by 1 over 2 to the n. So now the denominator in this error formula is a rapidly growing function of n. We have a factorial and an exponential, so that's nice. Using a Chebyshev points as interpolation points makes this part of the error manageable. We can control its size. The error can still get large because of the n plus first derivative, but at least we'd be able to win half the battle. And because of this, that Chebyshev polynomial, which has this factorization, but because it's a cosine, is also less than or equal to 1. And that's what we got. So any questions about how this result was arrived at? Okay. Actually have time for MATLAB part of this. Okay. MATLAB. Diary. And I'll be posting this diary in Canvas. So if you're not able to follow along, you'll have all commands accessible later. Okay. So what I'm going to do is I'm going to set the number of interpolation points, make it individual, to be 20. So k is going to be 20. Okay. And then I'll define a vector of indices from 0 up to k minus 1. So 0 to 19. The transpose is not really necessary, but I like working with column vectors instead of row vectors for printing things out. And now, if I go to the formula for the Chebyshev point, back here, the interpolation points are equal to the cosine of these angles for j going from 0 to k minus 1. So I'm going to define these angles. Okay, so theta, I'll define to be 2 times j plus 1 times pi over 2 times k. Okay. And then what I'll do is I'm going to plot cosine and sine of these angles. So you can see the points corresponding to these points in the unit circle that correspond to these angles. So cosine theta. I'm gonna make sure I don't have any existing plots. Close all. Okay, so then we have plot cosine theta, sine theta, and I'm gonna plot them using black circles. So K is for black, the O is for plotting circles.
Close all.
Yeah, that just closes any figured windows you might have open. It seems I always have plots open I forget about.
Wait, where did close all go?
As long as it's before a plot statement, it doesn't matter where it goes.
Close.
Okay, so here, now, I'm gonna adjust this plot window because the scaling on the X and Y axes are not the same. So I'm gonna stretch this a little, actually, I need to contract it. Oh, wait, no, I need to stretch it. Okay, so what we have, this is the top half of the unit circle. Now, if I do the following, diff of theta. What diff does, when you take diff of a vector, it will generate a new vector, but it's the difference of consecutive components of a vector. So if I do that here, all the values are the same. In other words,
Yes.
the angles are equally spaced.
Mine's in format short, not format long.
Doesn't matter. In fact, in my diary, if I print it out here, they are in format short. Okay. So now what I'm going to do is, here I have cosine sine of these angles plotted on the unit circle, but what I really want to do is I want to just the x values. So I'm going to, do a hold on. And then I'm going to plot, first I'll set x equal to cosine of the angles. So these are the Chebyshev points. So then I'll plot, and what I'm going to do is I'm going to plot these x values on the x-axis. Now what I really need is I need a zero vector that's the same size as x. Easiest way to get that is I can do 0 times x. It gives me a vector of all zeros, same size as x. And I'll plot them using red circles, so RO. So now we have the x values from these points in the unit circle projected onto the.
Mine did not. Mine didn't plot the way I had expected. Look.
Oh, you forgot to do a hold on. Wait.
Did you?
Oh, okay, but did you plot the black circles first? Wait, okay, close the window. Use the up arrow, go back to your commands, use the up arrow. No, I'll need to scroll up. Use the up arrow. And find the first plot command. Plot, do that.
I did.
Go ahead and do it. Right. Yeah, sure. Okay, now you hold on. No, don't close it. Don't close it. Hold on. Okay, all right. Okay, and then go to find the other plot command. Oh, yeah. Okay. Yeah, that. Go ahead. Yeah, sure. Okay, now go back to your plot window. Yeah, there we are.
Yeah, I did not understand what had happened here.
Okay. Now, but here it's, you can't tell that the x values are underneath the corresponding points, but it doesn't really show very well. So I'm going to add something to this plot to make it easier to see. So I'm going to start a loop for I equals 1 the length of theta. So I'm going to loop over all the angles. And then I'm going to do a plot. I'm going to plot vertical lines. So vertical lines have the same x value. So I have plot square bracket xi. Okay. And then I want vertical lines that will start at the x-axis and go all the way to the corresponding point on a unit circle. So the starting y-coordinate would be 0, and the ending y-coordinate would be sine of theta of I. And I'm going to plot them using blue dashed lines. So I put B dash dash. Okay. Now, this plot statement is inside a for loop. So now I'm going to end the for loop. And if I go back to my plot,
And
there they are. So see, we have blue dashed lines connecting the Chebyshev points as they are on the x-axis to the corresponding points on the unit circle. So basically, you're taking points on the circle at equally spaced angles and then projecting them down to the x-axis, and you get Chebyshev points. And notice that the Chebyshev points are clustered near the boundaries, -1 and 1. So they're closer together at the extremes, further apart in the middle. And that helps with reducing polynomial interpolation error. Any questions about how this graph was produced? So now I'm going to show Runge's example. Okay. All right. I just want to show you using both equally spaced and Chebyshev. So first, what I'll do is I'm going to define a function f at sine x to be 1 dot divide 1 plus x dot squared. I'm using the dots because I want to be able to plug a vector into f of x and have it work. Okay. Now, I can define, I have x defined to be my Chebyshev points, but I need to find another x dot x vector. X1 is going to be -5 to 5. These are equally spaced points. Okay. And there are 11 points in total, so this is going to be a degree 10 polynomial. And then I'll define y1 to be f of x1. So x1 and y1 are my interpolation data. So I can use MATLAB's polyfit, x1, y1, 10. So this gives me the interpolated polynomial for equally spaced points. Okay. Now, before I graph that, I want to have a similar polynomial for Chebyshev points, but of the same degree. So I'll define x2 to be the, okay, so I have cosine, same formula for Chebyshev points. I used this formula earlier with case of 20. Okay, so these are, now Chebyshev points, so those are from -1 to 1. I need points that distribute the same way as Chebyshev points, but on the interval -5 to 5. no problem, I just multiply by 5.
We're extrapolating.
No. I'm still only care about what's happening between -5 and 5. So these are scaled Chebyshev points. And I'm gonna have it print out. So what we see here, these are the Chebyshev points. And notice the ones in the middle, they're pretty far apart. 0 to 1.4 to 2.7. But notice they're a lot closer together near the boundaries. Okay. So now I have my x values, I need my y values. So I plug the x values.
Wait a minute. Something's not right. Why?
Yeah, that's fine, you can just repeat it by, don't do that.
Sorry.
Oh, you need the asterisk. Do it again, put a star after a 5. Okay.
What did I get wrong?
I'm not sure. 2 oh, not 2 divided by 11, it's 2 times 11. Okay. Okay, go ahead. Yeah, those are right points. Okay. So now that I have my Chebyshev points, I plug them into F, get my y values. And then I call polyfit again. But with x2 and y2, still degree 10. Number of interpolation points is the same. So this is the interpolant for the Chebyshev case. Right, so now I have 2 interpolating polynomials, both of degree 10, one for equally spaced, one for Chebyshev. So now what I want to do is I want to plot the function f and both interpolating polynomials in the same graph. Okay, so I'm going to create a new figure window, figure 2. Okay. Now, if I evaluate these at their respective interpolating points, so does degree. So I need a new vector of x values that has a lot of points.
It's not giving me a figure. This thing's not giving me a figure.
Oh, yes it did. Yeah, it's a new figure window. I just haven't put anything there yet. Right. So I can find the vector xx to be, I can use a command that we saw in homework 1, linspace. -5 to 5. Now by default, linspace will give me 100 points. Yeah, well, I can use 1,000. So I have a really smooth curve. And this is for plotting. Okay. So now I'm going to plot all 3 functions using xx. So first I'll plot f.
Something's not right.
You had an extra parenthesis.
My x wasn't in parentheses.
No, the parenthesis before then. Get rid of that parenthesis. Before linspace or the symbol there.
What did you mean?
Whatever's before linspace, get rid of that. Yeah, okay, go ahead. Yes, go ahead. Yeah. Okay. All right. So now I'll plot my function. Okay, there it is. That's the function we're trying to approximate. And then I do a hold on. And now I'm gonna plot XX, and then I have to evaluate these polynomials. Polyval, first it'll be equally spaced one. Polyval P1 XX. And I'm gonna do it in red, so dash R. Okay. And here we see, so blue is the original function, for red is the interpolated polynomial in the equally spaced case, and you see, even though it agrees with F at the interpolation points, every integer, it's way, way off in between. So that's not good. So in general, you're advised against high degree polynomial interpolation with equally spaced points. Oh, did it not? Oh, okay, that's front graph. Okay, now I'm going to plot the Chebyshev one. So I'm just going to change P1 to P2 and change the color. I'm going to make it green. Actually, I'll make it, yeah. I'll use C for cyan, so nice bright light blue. Okay. So here is, I'm going to make it a little thicker. Okay. Actually, I'll make all three graphs thicker.
Thick.
Yeah, you can right click on it and select a line width of 2. Okay. That'll make it a little easier to see. So the light blue one, that's Chebyshev. Now there's still noticeable error here compared to the blue ones, but it's a whole lot closer. The error is contained. It's not like going all over the place like the equally spaced one is. So Chebyshev is a whole lot better in this case. So that's why it's Chebyshev polynomials are popular for a lot of things because of their approximation properties. Okay. And that's actually all I have for this MATLAB demonstration. What I'm going to do is I'll post a diary, but I'll also post this figure. I mean, both figures. Okay. So do I have both? Yes, I have both. Okay. Okay. So yeah, the next homework due date is not for another week, the 24th. I mean, due dates being what they are in this class. But does anyone have any homework questions?
I still haven't gotten back to mine.
Okay. I'll be ready for when you do. Oh, we have one more interpolation topic. That's for Thursday. That's so 7.5. Oscillatory interpolation. We no longer assume that the x values are distinct. It seems kind of weird, but something good comes from it anyway. I guess that's it then.
So gives